Welcome, everyone, to the first lecture of the SCI-Arc lecture series, 2018-19. Tonight, we have Alisa Andrasek, who comes to us from RMIT. Many of you, I know, already know her, so I don't really want to read her bio. And anyway, you can look it up on your phone. So I just want to say a couple of comments before she gets up here. Some architects believe that architecture is constituted by a lot of stuff accumulating in various ways. While I don't think he was the origin of this thread, I'd like to argue that Jesse Reiser was an instrumental figure in making us think differently about little things and their relation to big things. In his article, The New Fineness, in Assemblage 41 in 2001, he laid out his argument clearest, although he was talking about it long before. He wanted to break down the mass of buildings into finer and finer parts to allow them to be able to register small differences while maintaining overall coherence. Coming off of the heavy cocktail of Pomo and Decon, this offered a way forward through a heterogeneous Deleuzian materialism that was able to contend with things like form, structure, and tectonics all at once. Please note that he did this before there was appropriate computation to support his vision. I remember an installation he did at Centre Pompidou, which had 1 million glowy magnetized parts. It felt like inhabiting a swarm field on its interior. Interestingly, it was not achieved by algorithm at all. It was awesome. Sometime later, Jesse abruptly stopped his work on fineness, announcing the swerve here in his lecture at SCI-Arc at this podium in one of the most authentic and cool moments I've seen of an architect changing course. Fineness was not enough. It had creeped up on him over time in his practice that things like structure did not tend toward heterogeneity, but rather standardization and economy. So during that same time, in the late 90s, another camp was developing, one that seemed related to Jesse's work, but with quite different rhetoric and intellectual justification. In this parallel camp, architecture was an evolutionary enterprise, and form was to be drawn from natural systems, literally. Natural systems constituted a new foundation for architecture. Architecture didn't come from architecture, but from the world. Architecture had to be as lively and seething as flora and fauna lying just outside the architect's metropolis. This camp has always been strongest in the UK and Germany, with outposts in Barcelona, now Australia, and even a few in the United States dotted along our East Coast. The binding idea then, as today, was that forces behind the things we see are what matter, not the things themselves. Today, this camp has become supercharged, which is Alisa's word, supercharged, with the availability of computing power and most perfect, or almost perfect, algorithmic simulation of material processes in the lab. Now, practitioners such as Alisa, also Roland, maybe Achim, Menges, and many others have the tools they need to realize the dream and possibly roll it out in earnest. But what was the dream again? Was it dreamier when the technology to execute it was primitive at best? Or is it dreamiest when it engages the global industrial complex and expresses itself in things like robotically 3D printed pavilions and houses? In general, what happens to dreams when ideas, techniques, and implementations are totally aligned in perfect workflows? Alisa's specific approach is to continue downward to ever smaller elements she calls high-resolution microstructures, as building blocks for larger things such as gooey layered robotic 3D printed things and fluffy ethereal cloud-like things. The way she writes about her work is telling. She tends to be committed to a technological and engineering origin story, but she also drifts occasionally into aesthetics, calling for fresh aesthetic possibilities or previously unseen aesthetics. I'm very interested in hearing more about the aesthetic drive here. What does it mean to see a large thing but also be able to read all of its discrete components? What does it mean if you can read traces of the tools used to make a thing? How does that bear on a thing's authenticity and presence? I like this quote I saw in Alisa's description of her enterprise called Wonderlab, which I like. So we shifted from Wonderland to Wonderlab. from imaginary land that was earlier just a matter of logical and poetic paradoxes, and that now can be engineered. So it seems that maybe the dream gives way to concrete reality. This is a decisive move away from the humanities, where art lives, towards the sciences, where engineering lives. I believe that despite this delineation, the best parts of her work lie not in the scientific realm, but in her playfulness, joy in naming and enchanting things like Wonderlab or like your office, Biothing, and in her unstated but obvious interest in contemporary aesthetics. It is those things that set her apart from others in her cadre, and those things that I'm most interested in hearing about tonight. So with that, I'd like to welcome Alisa to the stage. Thanks.
Thank you, Tom. Beautiful introduction, and thank you for reminding me of some of my family, or what I consider almost parents in the late 90s at Columbia when I was a student, such as Jesse or Carl Chu, Greg Lin, people that were investigating at the time lots of things, but basically developing a dream, as you're saying, that now is becoming more and more materialized, even though I wouldn't say it's perfect or seamless. There is lots of friction in the current stage. But I will just start, and thank you again, everyone, for coming tonight. Bear with me, I never know how my lectures will go when I'm severely jet-lagged. I just flew from Australia, but let's see. And so I just want to briefly introduce what's the concept or core of my work about, because I always thought if architecture has one superpower, that would be the power of complex synthesis of multitude of agencies. This is historically, I think, somehow a special skill of architects, that they always have to work with multitude of elements and bringing them together through design into coherent whole. Coherent or less coherent. Whether this is modes of, and constraints of constructibility, economy, certain gestalt of the time or thought of the time. Throughout history, we always find languages of architecture happening in a kind of polyvalent milieu. And so, but what is happening lately, I think, is that that synthesis is possible to become more explicit, encoded, and therefore processed more directly rather than just metaphorically as the certain encoding of architecture that was present historically, certain parochial models that were bound to more deterministic models of typology, production, notions of metaphor, and now I think we are coming to the point where we don't need to compress that information anymore. We can work with it directly. And as Tom mentioned, my research lab in London was called Wonderlab in the past 5-6 years. And the reason why I'm interested in this idea of wonder, unseen, is because I'm always intrigued by the future of beauty or aesthetics that are unseen, and how we can render these invisible forces visible in a kind of hybrid cognition, I would say, that is starting to develop, which is very much human, but it has this other as well working within it. And so this concept of increased resolution in my mind when I started my practice Biothing in 2001 was bound to increased modes of computation or increased volumes of computation available. And what you can say Turing gave us, which is this idea of Turing enhancement or accelerated time. And even in the 40s during the Second World War, when he was breaking Enigma code, certain operations would take maybe 5 million years to humans to do by hand, and would happen even at that time within 1 day because of the power of computation. So a quick quote from Daniel then is what Turing gave us is a way of thinking and taking seriously phenomena that has trillions of moving parts. So this type of increased resolution, like in a desert dune, when everything happens through physics, We have frictions of grains of sand, we have temperature, we have pressure. So everything is intensive computation, there is or material computing. And this is Jesse Reiser's reference on materialism, which was very influential of me when I was a student. And also what I like to look at is always the first principles. Sometimes I like to forget about history a little bit because I was actually educated in Zagreb on a kind of rich tradition in Croatia, in my home country, rich tradition of modernism initially. So there was a quite thick fabric of architectural history. And then at Columbia as well, when I was studying, there was expansion into that, but sometimes I like to look directly. I'm very much always inspired and use physics underneath my work quite explicitly and think about first principles and how can we rewrite certain rules in architecture or ask the question even what architecture could be. So for the first time in history, we can build with building blocks that are at a resolution of specks of dust, or we can work with trillions of elements. So we never had access to that before. So I think it's a right time to ask what architecture could be in this kind of condition. And we see that in the car industry. McLaren, for instance, is simulating cars and their processes for Formula One, and the process is accelerated radically, because in the past it would maybe take the whole year to develop a couple new components for Formula One, and now it maybe takes a couple of weeks or less, because we can simulate not only these cars running through a wind tunnel, but also exact physics of exact materials used, obviously all the geometry involved. So computational physics is something that I like to use a lot, and what I call algorithmic profile of matter. Another area that I use a lot is things like behavioral systems, such as multi-agent systems that have ability for a local adaptation and local intelligence. And when I looked at natural systems, because I was always, my initial question was so how do we address complexity heads-on? And when I looked at natural systems, complex systems, and also acute systems in technology, and we can see that especially recently with the development of machine learning, artificial intelligence, it only became possible in the last few years because the volumes of computation increased so radically. So for me, this topic of resolution emerged very early on as a kind of, as important. And this is a little quote from my PhD even, and while for Wim Koolhaas, in his masterly absorption of modernity, elements of architecture appear at the resolution of doors, floors, windows, etc., this work makes an alternative proposal to re-originate architecture's fundamentals. It wants to introduce the physics of friction, gravity, viscosity, and massive volumes of data and code as the acute fundamentals of the new kind of architecture at increased resolution. So, I mean, of course, Rem is his brilliance, but he's very much versed into or expert in modernism, and almost a kind of a manneristic way, very playful way working with modern. But I think at this point we can propose something else. I think modernism was a very successful period in architecture in many ways, but with the current knowledge and current resources, I think we can start to think in expanded and renewed origins. And the way I practice is always kind of as a distributed operation. My research, academic research, technology research, or teaching is always running in parallel or through also my practice, Biothing, or different startups such as Bloom Games and others. I was one of the founders also of AI Build that is now very successful in London. And I also sometimes like to curate events where I invite many of our friends, some of people from here as well, to discuss some of the topics that are on the table. So this kind of intellectual discourse is very important. But what I would say is the main characteristic from the beginning of my practice is that kind of computational core, so the logical core of architecture that I actually think always existed in one way or another. And that was my focus. And through that logical core that is algorithmic in nature, everything else gets bound and accelerated and synthesized in this kind of open synthesis. And I'm interested in this extreme abstractions, but also in open forms of synthesis or formalisms rather than closed. So what does that mean? If there is one feature of my work with algorithms that could be tracked throughout my work is that it was always increased discretization, because I was educated by the generation of thinkers in the 90s that were very much interested in mathematics of continuum. And when I was trying to think about complex systems or looking at in science, or even thinking about the skin of the building, for instance, interfacing something like weather that is extremely nonlinear, these kind of linear functions were just not cutting it. So I started simplifying building blocks of logics into more and more discrete elements. And I don't know, perhaps there is no time now to go through this sample from the history of my work, but there were always next algorithm that is based on dumber and dumber, you can say, simpler, more elemental particles of logic. But because of that, they are able as a collective to reorganize and emerge into complex behaviors at a higher level. So this is maybe the main feature. And a recently published book by Mario Karpov with our research work on the cover is also talking about this idea of the second digital turn, even though I don't embrace the word digital so much. I think it's limiting. But the idea of this kind of discreteness, and that we are approaching the point in history where the compression of information of data, such as, for instance, mathematics, a model of compression. We need to write formulas to explain certain phenomena. It's ceasing to exist. The need for that ceases to exist because we can now simply simulate the physical events as they are. And so that's the kind of line that I've been exploring for the past at least 15 years, or trying to get closer to that. And I always like remembering this initial exercise that became one of these projects for the London Olympics, Bloom, which was my exercise with students. Maybe I invented it in 2002 or something at Columbia when I was teaching there. And I was trying to introduce students into logics of computation, rule-based systems. So the task was to develop one single component out of, let's say, rigid material, and just focus on the connection points. In Bloom, you only have 3 simple vectors, 3 connection possibilities. So it's very discretized and universal element, but whenever someone plays with this toy, it becomes something else. I rarely see 2 same outcomes. So that kind of logic of complexity for free, or really simple building elements that then can emerge in. And in the case of Bloom, this was designed for the London Olympics in 2012, and there is no blueprint. It's been in over 30 countries now, and when people start playing with it, there are no instructions. They just improvise. So the energy and the blueprint of the game comes from the play itself. Yet it always emerges into something else. And it also came out of my frustration with linear parametric functions, where I would try to develop, and I don't have time now to go into that, but I would try to prototype some elements of architecture, and then if you're using, for instance, sine wave functions or gradient-based formulas, you have to connect every element in exact position, otherwise there is no tolerance, the whole system collapses. In Bloom, there is just improvisation and similar systems, so there is a strong adaptation feature here. Of course, people like to project their representational. This was quite a surprise for me, because we designed just, with Jose Sanchez actually, who is now based in LA, we designed just abstract little construction game, almost like Lego, old Lego, just universal elements. But kids especially projected all this kind of all these monsters, dragons, and things like that into it, and grown-ups as well. I mean, this was really strange, but fun to see. And again, Bloom's been in many places. This guy made a friend And then it became also Baby Bloom toy that, so that was just, I only mentioned Bloom. It's a very simple project, but because it's based only on that simple logic, that discrete elements and very simple things can create very complex effects. And this is another project where I just wanted to run through a couple of, and it's quite old now, maybe 2010 or something, but use of multi-agent systems, for instance, in this kind of, with this adaptive quality, but also certain aesthetics that one could say these logics are based on simulations of natural systems, but they are extremely unnatural and sometimes weird. So this was a competition in Kaohsiung in Taiwan for, I think Tom did it as well, I'm not sure, for a big port terminal, and quite long building, around 350 meters long. And I was looking into Kaohsiung as, because it's a tropical climate. I've been to Taiwan a few times. And people like to be outside, especially during the night, because during the day it's too hot. So I tried to develop some exterior spaces, and I cut this building into almost like canyons, these slits that are 35 meters tall and 300 meters or 350 meters long. So also to introduce, to increase the circulation of air, almost create a wind to the building, to create a certain microclimate. So, and also at the entrance of Kaohsiung, you have this kind of iconic cliffs. So I thought like we resonate certain feature of the local kind of landscape. And then I spoke to Reader, this company in Austria that is doing Fiber-C. They're doing this kind of glass fiber reinforced concrete panels for facades. And I asked them what are because they are one of the most advanced, probably, manufacturers of facades in the world. They worked with Zaha and many other architects. And so they told me that basically I can make every panel different as long as the horizontal datum is stable. So this can move in 2 axes. So multi-agent system was programmed to move in, for instance, X and Y, but not to touch Z, because if underlying structure goes into Z direction, then it becomes irrationally, for instance, expensive. But this was already lots of freedom, because then we got this kind of unnatural canyon-like formations, almost like a stone formations, and they were treated in different materials through the building. So when you arrive to this, I'm trying to see where is my, seems like I forgot to, yeah, here. The first canyon, you are entering the building and there is a big wave coming below the facade and splashing into the, so there is a certain sound event, and it was also, engineers wanted us to also explore generating energy with that. But anyhow, I just thought each of the environments, they are like these parallel realities, quite radically different one from another. And this was a concept for this building, and there was an interest in exploring different material treatments. And then other use of multi-agent systems in this building was navigation, because I was reading about these insects in Africa. When the storm is coming in, they start to glow over tens of kilometers of a landscape, and you get this kind of almost another layer of a weather event. So I was thinking about buildings like airports and these kind of port terminals where you have to find different gates or your way, and you're following the signs. So instead of following the signs and this kind of on and off switches in building, I was wondering what can light or lighting systems be in the building. So of course I was obsessed with these YouTube videos of slow down lighting actually, and that was an inspiration for programming the agents to crawl through the building to develop high resolution structure that would carry light events. So when you arrive here, the structure starts to glow and intuitively lead you through the building. We did not get that competition, but another example of another competition we did not get, but it was interesting, again, use of multi-agent systems. This was in Dubrovnik in Croatia, my origin country, and there was a design of this plaza behind the city, and the goal was to, and we used some computational systems like n-dimensional sort of cellular automata that was programming this urban landscape, including structure, including lighting elements, planting elements, even misters. So everything was encoded into data of CA in this case. This sort of urban villas that are part of the project were also programmed through multi-agent systems in a way that I was thinking about Mediterranean culture of living. People like to be outside. Also, this particular site had really good views in front of the sea and old city. So agents were programmed to negotiate multiple elements, such as views, orientation that is quite complex, and also at the time I was thinking of Peter Eisenman's kind of earlier period where he was working on, for instance, House 10 and this other complex work with a section. So this was almost like a bastard child of a little bit of features of Peter Eisenman's section, and then this Mediterranean patterns of living, and trying to program agents to seek, like this seagrass almost, multiple elements. So this is not a kind of parametric linear gradient. This is a behavioral model that tries to negotiate multiple adaptive elements on the site. And as a designer, and I always work a lot on design interface, I actually spend more time on design search, and this is related to aesthetics, because I actually invest a lot into that part of design process. So we always incorporate many elements for this. And then, but also when it's almost a little bit like working with the DNA, because that same behavior could be applied to another project. This was another project for a small tower in Montenegro, just next door. So in this case, it was a very similar goal, but in a different typology of building. So this kind of knowledge or systems learning keeps propagating. And in 2001, I said, I don't know, quite interestingly, only today we can think about this in terms of AI, but I said that the main goal of my practice was also to not only evolve our knowledge of this kind of hybrid sensibility in touch with computational systems, but also for it to learn. And learning is becoming a big part of design process, a learning of systems learning as well, not just us. Another quick project, I'm not going in depth into these projects just because I want to show you different scales as well of application of this work. This is a quite large macro scale, and it was an invited competition by Kengo Kuma and Tadao Ando in Osaka for a center of the city. And when I was reading the brief, which was very lengthy, one thing that jumped at me the most was that every day this site is traversed by 2.5 million people. Now that number does not exist. I mean, I was looking into, for instance, central London, and barely you can say that many people pass through central London every single day. So it's something that was very abstract for me, and as a kind of master plan urban proposal, I thought that this is by far, I mean, this site was very, very complex because it had a massive bullet train station, which is one of the biggest in Japan. It's probably the biggest, I don't know, it's with Tokyo, the biggest one, and all sorts of very charged programs around. So it was a very complex site, and I thought, well, I will actually quite literally treat this river of people as a river, and we will use computational physics and simulate on this site through fluid dynamics how this mass of people would move. So we use multiple algorithms, of course. One was simulations of computational physics to see if it would be like a river finding a path of least resistance to the landscape, what would happen and how the site would organize. So things like this started emerging. They started looking like desert dunes, also because I didn't want to do towers on this site. I thought after the big earthquake, it didn't make sense. But in the end, towers won the competition. And here, we just got some very elusive massing through physics that we used as a base for modeling this massing of, these are 7 floors high buildings. But we also worked with engineers. We were working with Biro Happold and Hitachi Consulting on this project collaboratively, and they gave us lots of data. So we were looking at different users and using multi-agent systems, how different users penetrate this site, and also 7 or 8 ways of energy generating, collection and generating. So one of the most interesting ones, I won't of course go into all of them, for me was the one using kinetic energy or vibration, because if you really have this number of people, it becomes significant. So usually it's not very useful, but in this case it was. So with engineers, we were looking into almost like a cloud structure, something that is a big structural field with different intensity or different density of structure. And in order to work with the Internet of Things, so there were lots of ideas about distributed systems that we worked with Hitachi, because I imagined this site not only as a massing urban proposal, but also as if you look at, for instance, Sagrada Familia or Gothic cathedrals in Europe, they were going on for a long time, and they were developing certain technologies, and this was the goal, to seed certain innovation through this project. So there were lots of technologies, but this piezoelectric tiling that was supposed to happen where people walk, I'm just trying to find some of the mappings. Well, these heat maps, they're small, but we would analyze through these desert dunes where they can actually, through inclinations, where they can walk and things like that. So that's where the population of this tiling was distributed. So we would get, from the simulation, we would get this kind of big data scenario with billions of particles, and then that would be plugged into algorithms that would weave adaptive structures. And then also ideas, I mean, it was a very intricate urban massing with many of these systems packed into that. So for instance, lighting infrastructure that is reprogrammable, water on the site, all sorts of things. So you shouldn't look at this as architecture, this is just massing, but it was sort of communicating these ideas of multi-systems. We call this urban operating systems. That was Biro Happold's term, but I thought it was interesting because it was understood as a completely programmable urban field. My signature element of canyons was also somehow part of this project as well. But, and I would like to show you more of my architectural scale projects, but because for the past 5, 6, 7 years, I was very much invested into, because after doing all these speculative projects at a very large and also middle scale of architecture, how do we build that? How do we build increase the level of resolution? And last year, there was this cover of Economist with some disasters on the top, on the cover, so obviously Trump, and then this line that construction, one of the biggest industries in the world, is also the least efficient one. So there is so much room to change, because when we look at the constructability with the construction industry, methods are so old. They're coming often from 19th century or earlier. So the use of technology is very scarce still. So in London, we formed, I was a founder, and I directed this research program at the Bartlett, where we tried to get lots of I was really looking for the best talent I could find, and we were lucky that they all joined, and one of them will be lecturing here, Gilles Retzin, later in the semester. But we really started as a group investigating different forms of constructibility with robotics, with algorithms. And I mean, this is quite obvious, but if you look at the resolution again at which nature built, like one obvious example that is often used is bones. So if you look at the bones in your body, they are denser in, for instance, the bottom of your leg because they carry more weight, or then in your arm, except if you're a very good tennis player, which I'm not, sadly. But if you look on the microscope at the collagen fibers, they form the skin, and then they reorganize into different patterns, and then they form the joint, and then they again reorganize, and they create the strength and resilience of bone. So monomaterial in that case, but performing radically different kind of super performance coming from science as a term that I like to use, because I really don't like these notions of optimization and performance that are so popular in practice these days, because I think that's really lacking ambition. At this point in time, we should be striving for way more than optimization and just a kind of classical engineering project. So these are some examples of these microstructures that Tom was also referring to, where myriad of algorithms are used to, some of them are instantiated for organization. So in this case, multi-agent systems is organizing structural veins. This is just a chair example, initial exercise, where students are looking into where the structure needs to go. And then voxelizing that information, voxels, this kind of n-dimensional points in space that are not only carrying information about X, Y, Z, but can carry data about lots of other features, such as which material is extruded at which speed and pressure, what's the relationship to other agents. Anyways, I always like to call it n-dimensions, which science regularly works with, because I think we need to go also beyond 3 when we are talking about data structures in constructed fabric or design fabric. And in this case, perhaps high resolution is also applied where the chair is touching the body to make it more comfortable, perhaps. And then that data is programmed for constraints of robotic extrusion, particular one, 3-dimensional extrusion of plastics in this case. So there are lots of constraints there, so you're working with another layer of data. Not to go into too many nerdy details here, but there is also, we wanted to work with a certain lattice structure that has certain micro transformations in it. So there are lots of layers of information. So this is starting to go into bigger data problems. And it becomes also, and this is something that I will focus on quite a bit in this talk, becomes quite opaque for human cognition to search through. Which is an interesting problem. It's an opportunity, but also a challenge. So another related project where instead of multi-agent systems, for instance, computational physics of liquids were used, so fluid dynamics, literally liquids were splashed around the body to find the shape of the chair, and then this was again transferred through various data layers, voxels, printing paths, and then in London, we were also producing this kind of custom nozzles always. Students were building these nozzles and then programming the robot to print some protostructures. Also, this is roughly 3 meters tall column. This one is a bit taller, I think. Another project from that series, in this case, I'm just giving different examples to also show how we can use a myriad of algorithms to find different aesthetic and structural expressions. In this case, noise was used, which is an algorithm I really love, because it's so hard to find beautiful patterns in noise or any patterns that are structural. It's a big challenge, but when you do find them, I think they're really next level. And in this case, students were looking, for instance, into example of protostructures such as wall or column. So at this resolution, not only the structural veins could be programmed, not yet at the level of the bone, but much higher resolution than the typical elements that we use today for architecture. But also the light can penetrate and be filtered in a kind of high resolution ways, again asking us what architecture could be. So if the fabric is this intricate, what can we envision as a, and also because, for instance, buildings are roughly 10 times heavier, if not more, typical building than they could be, according to if you look at some systems in nature or laws of physics. So I think we need to do better with all the knowledge and resources we have right now. We cannot build as we did in the 19th century. This is another, again, example of layering data. We don't have time now to go through this. So different fabrics pattern in different ways. And this project was done for the Venice Biennale, the Croatian pavilion at the Venice Biennale this year. If some of you have been there, maybe you've seen it. It was a in Arsenale. So based on this kind of lattice research, I looked into creating a structure in the pavilion space which would be very light. I mean, this whole structure is 8 by 8 meters in plan roughly, and around 3.3 meters tall. So it was only 275 kilograms, the whole structure. So engineers were telling us this is as light as one can get with structure. Only fabrics could be so light. Yet is incredibly strong, even though it's printed in plastics, which is, I mean, obviously a proxy material still, but something we had access to. It was printed by this startup I mentioned that came out of my research lab called AI Build. And in this case, multi-agent systems were used to spin and counterspin these elements, so they increase in structural resiliency, but they also give certain intricate expression. When you're in this space, you almost feel these forces pulling you around. It's like being in the forest. And of course, initially, I designed something that had 500,000 voxels. But because of the printing time, we had to reduce it to 40,000, which was the maximum printing time we were able to get before the Biennale. And so we created these 3 chunks. And there was also beautiful, 2 artists were also in the space. One was working with sound, with a kind of interactive sound, which was of a very similar nature and programmed in a similar way like the structure. Also, the light was programmed almost as a kind of very ambient and almost like artificial weather in some ways. So, but what happens now when you are working with 500,000 voxels? Again, it becomes often opaque. The design search process is incredibly demanding. So the automation is a topic I'm trying to work on more and more. And in some ways, algorithms already automate. There is always this hybrid design agency. So generative, I mean, we would always say that generative design allows you to design beyond your initial imagination. So you're kind of searching, you're working with it rather than just controlling it deterministically. But now with artificial intelligence, this is being accelerated. So there are a few topics of research that are on the table right now. Some are really optimization topics, such as how do we print with robots so they start being more aware of what they are building. So this was an example. We worked also with the AI Build to do this, to use deep learning to teach the robot what the node is. Now, this was a very kind of laborious process still for humans, because a human needs to teach this this algorithm. Well, this is a node, this is a node. So after 10,000, this is a node, it starts understanding what the node is. But once it understands that, there is no way back. It will always snap to the node, which kind of accelerates the process of production and starts working with materiality, because materials work, they are not, there is a certain contingency. Contingency is incomputable, of course, and I don't know if it will ever be computable, but this chance and the kind of nonlinear behaviors of material need to be taken into account, and it's really a topic that interests me. So the machine learning in this context is interesting, but it's quite optimizational application. Or here we were working with collaborative weaving of robots for carbon fiber structures, which was very complicated. So again, starting to develop certain machine learning awareness and computational vision. But my main actually, and this relates a lot to the aesthetics that Tom was mentioning, because it's actually a strong interest of mine, always was. I always actually openly admit it, even though in architecture, for some reason, that seems to be forbidden topic for some reason. But anyways, I'm interested in hacking directly into creativity, and I had this sort of talk with some UCL computer scientists about this, and 3-4 years ago, and they told me this is crazy, this is 30 years ahead of our time, and I said, well, I think we can start working on this, and we see some initial attempts. Some people are working with deep learning and etc. I was collaborating with Andy Lomas, who was part of my research lab in London. And we were both interested in design search throughout our whole work, and we are both very high resolution. So when you have this sea of data, this ocean, and you dive in, there is really a challenge to find certain sequences that are very hard to find, this kind of pattern recognition problem. So in this case, it was the idea of supervised learning. I don't have time to go through all these theoretical issues, but for instance, in this project, it was a very high resolution using cellular division. This is a kind of logic that cancer cells use to split, but also in, for instance, embryogenesis, all our bodies and the body of giraffe and every other creature is formed in this way, through cellular division. So it's quite powerful algorithm in a sense that it can almost develop any kind of body plan or pattern. It's very smart. But it's also very hard to search through. And Andy Lomas also works with this. In fact, he brought it into the lab, and then we worked with students on some architectural applications. So in the past, we used to work through these catalogs and just track different parameters. It's a feature of parametric architecture especially. It's just that the level of data is so huge that if you have a parametric space of, let's say, 40 parameters, it becomes impossible to search. So then this was a first kind of simple example of, not so simple, but it's supervised learning. So you, as a human designer, is telling the machine learning algorithm, I like this, so you evaluating this 1 to 10, let's say, giving it some sort of scores, and then it starts searching, it starts accelerating search for you. It dives in there and finds more of this. So I was very intrigued by this because I was thinking, okay, so I have very strong biases as a human when as every, I think, intense designer, we are all a bit control freaks, which you have to be in order to find an expression. And I was interested to develop this and give it to my friends with strong eyes, such as Tom, Elena, and everyone, to really strong designers initially, to see how we can somehow create this, again, bastard child in a kind of embedded with very different sensibilities, but very biased ones, before we unleash it to the world and see what happens in terms of what kind of aesthetic biases it will start producing, apart from just the functional sort of helping you to search for certain designs in large data context. This is also cellular division algorithm, but with one dimension less, 1 or 2 even, applied to layer by layer printing, so it's only splitting this kind of strings. There are lots of material constraints when you're working with this. For instance, if you're printing with plastic versus clay, there are different angles of cantilevering that you can use. So lots of information needs to be embedded into the algorithm. This was students producing some furniture pieces. In London, we produced lots of furniture pieces because it was something that we could immediately fabricate with the scale of robotics we had. This was another iteration of the same algorithm, just a little modification in behavior. We printed some, this was in Melbourne last year, printed some urban kind of benches, this was 3-4 years ago now. This proto-column was shown at the Centre Pompidou and ZKM in Germany and other places. It was printed in 2 materials because we developed these nozzles that can print multiple materials. Somehow I don't have a video of the process here, I apologize. But so I wanted to, in this case, we were just mixing the color. It was plastic, but in 2 different colors. And so this project is very risky. It's only in its infancy, but I wanted to show it because I think that's where we are going next in some aspects of the research, which is we tried to go for more radical automation. And we were wondering, can we bring a space of design and constructibility in one algorithmic space through some rudimentary machine learning? So in this case, we were looking into dance. Students were looking into William Forsythe's choreography, where certain movement is conditioned rather than prescribed. So I'm sure you are familiar with this, but dancers are instructed to run against each other at the highest speed, or they interact with architecture. For instance, he worked with Daniel Libeskind on this, so bounced off the walls, or some sort of conditioning of movement is part of the choreography, very Deleuzian actually. And so students were programming different movements of the robot, so the way the robotic arm moves, so they were simulating it together with material behavior of plastic, and also different speeds and different pressures of extrusion. And so they got different, quite noisy fabrics as a language of what kind of materiality comes out of just different behavior of the robotic arm. And then we asked the robot to design and produce a table. This is quite a simple thing. So print it upside down, and we had to still mathematize this conditioning. So tell it that it needs to design and print a plane, and then start recognizing through some 3D scanning, like through Kinect, where is it now? Start recognizing peaks in this field and start building off these peaks, basically building legs, and then at some point to stop at the same datum and then flip it around and we get a table. Of course, these things look horrible. No human, it was just basic conditions, so no human designer was involved, so you get very ugly first results, but I thought it was interesting. Lots of noise was involved in this. And also because, and this is something that Benjamin Bratton talks about a lot in a very interesting way, for instance, his lecture on synthetic vision, where, for instance, there are completely different senses that machines have than we do. So for instance, the dark factories, the robots that are working in the dark, etc. And throughout history, and I really recommend this lecture by Ben, we can kind of find different models of this synthetic vision. So for me, this kind of idea of different cognition being combined with ours and trained by us and imprinted by our sensibilities is very interesting. And then what happens at the intersection? In a way, it's just extension of algorithmic design that I've always been doing. It also designed some sort of table, I think. And I will just show one more example and then open it to questions, sampling a little bit through this high-resolution fabric. This was another project for a tower, and looking at the regulations for building skins in Europe have changed 4, 5, 6 years ago, and they're asking building skins to perform at much higher levels. So we were wondering, we spoke to some industry in Spain about this, and we were wondering whether we can talk to the industry, what can we change in these skins? So they asked us to please not change the connection parts to the buildings, but to maybe play with 3D printed panels to kind of filter light or other aspects differently. I'm trying to find a video here. And so we looked into algorithms for stigmergy, which is also agent-based system, but a different one than a swarm. It happens in, for instance, termite colonies. Oh, I didn't want sound. And so basically termites are signaling with pheromones, and they develop these incredibly intricate termite mounds. I think this example has been used in architecture many times, but just the feature that you can develop this kind of very high-resolution light filter in this case, and it was applied to the tower. This one is going very slow, so maybe I just rely on slides. So something like this was a result of simulation with agents somehow reacting to different light conditions in the building. And then we tried printing that, and it was too high resolution data field. It wouldn't correspond to robotic or material condition in reality. So we recomputed that data into lower res of robotic paths, and also while optimizing robotic paths to move without collisions and as fast as possible through pathfinding logics. and that was structured to this voxelized space, so discretized space. So suddenly, completely different aesthetics emerged. And I was imagine this tower if you're driving, let's say, somewhere, and from 2 kilometers you see this tower, and it looks like some strange plant on the building. And then you come closer, and it's very much like this Minecrafty aesthetics, almost completely discretized, and it's a completely counterintuitive. This is what I mean by unseen aesthetics, or something that is actually deeply unnatural, even though it resonates some logics from natural systems, some abstractions. So I'm very much interested in this idea of what the future of aesthetics could be. And I also think that aesthetics, as I briefly showed through design search examples, is that bridge between the two types of cognition and the hybrid cognition that I think we are interested in, between the human and inhuman elements. So I would probably close here and open this for questions, if you have any questions. Thank you.